In today's video, let's talk about using a detailed example to explain the concept of worst-case running time for a randomized select algorithm. So first we set up an example. Let's consider we have an array A. So initial setup, array A has element 5, 2, 9, 1, 5, 8, 3, 7, and 6. And we try to find the minimal element, which is I is equals 1, which means it is the first smallest element in this array. The first recursive call, let's assume that the pivot is randomly selected in the first call, which is 9, which is the largest element in our case. So the partition result we get is left side is less than 9, which is 5, 2, 1, 5, 8, 3, 7, and 6. And the right side is empty, so the pivot index q is equals 8, and the number of elements on the left of the pivot is k is equals 9. Since I is 1 is less than k, which is 9, so now we just recursively search in the left subarray and ignore the pivot. And then the second recursive call, we assume the pivot selected now is 8. So now the new partition result is left side is 5, 2, 1, 5, 3, 7, and 6, and the right side is still empty. So now we have the new pivot index q is equals 7, and since I is equals 1, which is less than k, which is equals 8, again, we still focus on the left subarray, and we continue this pattern. So each pivot selected in the largest remaining element, and each step reduces the problem size by only one element, which is the pivot itself. Let's try to analyze the worst-case running time. So each partition operation takes linear time, which is theta of n. The theta of n time is to partition the n elements, and the t of n minus 1 is recursive call on the remaining n minus 1 elements. So the recurrence relation which describes the worst-case scenario is t of n is equals t of n minus 1 plus theta of n. So we try to solve this, we have to expand in the recurrence, which is t of n is equals t of n minus 1 plus theta of n, which is equals t of n minus 2 plus big theta of n minus 1 plus big theta of n, which is equals ellipsis, which is equals t of 1 plus the big theta of 2 plus ellipsis plus big theta of n. So this led to a summation of cost, which is the sum from k equals 1 to k equals n of the theta of k, which is equals the theta of 1 plus 2 plus ellipsis up to n, which is equals the theta of n squared. Thus, t of n is equals theta of n squared in the worst case. This example demonstrates how selecting the largest remaining element as the pivot each time resulting in the maximum number of recursive calls, with each call reducing the problem size by only 1. So it illustrates why the worst-case running time is theta of n squared, which is similar to the worst-case scenario in the quicksort algorithm. However, because of the randomness in pivot selection, this worst-case scenario is highly improbable, which leading to a linear expected running time in the most practical situations.